This video is for problem set 32. We're going to start our discussion of thermodynamics, which includes, first off, talking about energy, heat, and work. And so let's get going. So first question asks, what's the first law of thermodynamics? The first law of thermodynamics is that energy is conserved. In other words, the total energy of the total change of energy of the universe is zero. So this delta, this triangle, that means change. It means final minus initial. And so the total change in energy of the universe is equal to zero. Now, what is the universe? We talk about the universe as meaning the energy of the universe is going to equal the sum of the energy of the system, which is just what we talk about and care about, and the energy of the surroundings, which is everything else. And so the universe is just literally everything. So a system can lose energy or gain energy, but that same amount of energy is lost or gained by the surroundings. All right, two ways to increase internal energy of a gas sample. We usually say that the change in energy is the heat change plus the work change. So this is heat, and this is work. Now for Chem 105, heat's just heat, and work has to do with a gas that's expanding or contracting. Okay, so in physics we talk about we talk about work being a force over a distance, or force times distance. But for chemistry, we talk about work. We care about pressure volume work, which is what comes here. We care about pressure volume work. In other words, if you have a gas sample, let's say it has this volume, okay, and externally we push down on that gas sample and we make it smaller, we've now done work on the gas. So we've added energy to the gas. So that work is positive if it contracts. If it expands, then the opposite is true. If we have a gas sample and the gas sample pushes out and expands, now the gas sample's done the work, it loses energy. So work is negative for an expanding gas, which brings us to C. C asks, why is there a negative sign on the P delta V term in E equals Q minus P delta V? Well, first let's define what is work. Work is defined as negative P change in volume, negative pressure change volume. And so then if I plug that in here, I get that delta E equals Q minus P delta V, which is what this is referring to. Why is there a negative sign in front of that term? Well, the reason is because work is negative P delta V, and Y is work negative P delta V instead of just positive P delta V. Well, we said that if a gas is expanding, we want that work to be negative. Well, if it's expanding, then V final minus V initial, which is delta V. If it's expanding, V final is going to be bigger, so this is going to be a positive value. But we want the work value to be negative if it's expanding, so we need to have that negative out front to negate that. And similarly, if we are contracting, then V final is smaller, which makes this value negative, but when we're contracting, we want work to be positive, so we have that negative sign in the equation to flip the sign. So it has to do with making sure the signs are correct. And then what's meant by a state function? A state function is a property that is independent of change. Or is not associated with change. So for example, volume. Okay, let's say that I have something that's 4 liters. So something that was 2 liters, and then it went up to 4 liters, and something else that was 2 liters, and then it went up to 6 liters, and then it went down to 4 liters. At the end of the day, they're both 4 liters. Is there anything different between their volumes? No, because volume is a state function. It doesn't matter how I got to the 4 liters. Once I'm there, 4 liters is 4 liters is 4 liters. That is a state function. So state function is path independent. Okay, a non-state function is just something associated with a change. So like heat and work, those are associated with a change in energy. So energy is a state function. Once I get to a certain energy, I'm there, and that's just what it is. But if I'm changing energy, how do I get that energy to change? That's heat and work. And so heat and work would not be state functions. All right, so we talked about work is positive when a gas is being compressed and negative when a gas expands. Heat is positive when the heat's being added to the system, and negative when the heat is removed from the system. When heat is being added, we call that endothermic, and when heat's being released, we call that exothermic. So here it asks, which of the following processes are exothermic? So exothermic is a negative Q, and endothermic is a positive Q. All right, rubbing alcohol evaporates from the skin. Okay, that is endothermic, because in order to get that rubbing alcohol to go from a liquid to a vapor, I need to put heat into it. Just like if you want to boil water, you have to put heat into it. So that's endothermic. And that's why rubbing alcohol evaporating from your skin makes your hands or your skin cold, because it needs to suck heat out of your hand in order to evaporate. Okay, fog forms over San Francisco Bay. Okay, so I've got this water vapor in the atmosphere, and then at night it gets cold enough and the conditions get just right where that vapor starts to condense into a cloud or fog over the bay. So that's going from the vapor in the sky to the fog over the bay, and so I'm going from vapor to a liquid is going to be exo, because going from liquid to vapor requires heat, so going from vapor to liquid is going to release heat. Okay, ice cubes solidify in the freezer. Going from a liquid to a solid is going to release heat. Ice cubes in a frost-free freezer slowly lose mass. So those are going from a solid, and they're actually sublimating to lose that mass. And so that's going to require energy to melt that liquid or sublimate it. Dew forms on a lawn overnight. Again, we've got, just like the fog, we have vapor, water in the vapor, condensing onto grass, and that's going to release heat, so exo. And then lastly, molten aluminum solidifies. Again, I'm going from liquid to solid, which is going to release heat, so that's exothermic. Okay, if the reaction mixture on the right is a thermodynamic system, and the pressure on the system is constant 1 atmosphere, what is the value of work? And then they give us the way to calculate the volume. All right, so we got to remember work equals negative P delta V, which is negative pressure V final minus V initial. Okay, and then we don't have volumes, but we have radius and height stuff, so I'm just going to put those in. Work equals negative pressure. V final is going to be pi R final squared H final minus pi R initial squared H initial. That doesn't look like a negative, it should. Okay, now we can plug in our values. So we know the pressure is 1 atmosphere. Okay, now I have pi. My final radius, so radius isn't changing, so my final radius is 30 centimeters. I'm going to change these to meters, so this is 0.3 meters, 0.4 meters, 0.27 meters. Okay, so then my R is going to be 0.3 meters. And my height is 0.4 meters minus pi. Oh, my bad. That was final. Should be final. So final is 0.3 meters, and my height is 0.27 meters, minus initial is 0.3 meters, and 0.4 meters as the height. Okay, so hopefully we get all this math correct. So pi times 0.3 squared times 0.27 minus pi times 0.3 squared times 0.4. I get equals negative 1 atmosphere times 0.0763 meters cubed. Okay, but I don't care about meters cubed. We usually like our work in either liter atmospheres or joules. So I'm going to change these meters cubed to liters. I know that there's 1,000 liters in 1 meter cubed. And now I can do this math. Okay, when I did that, I got, oh, that's what I did wrong. Okay, I just noticed that where I typed something in my calculator wrong. So I'm going to type in this stuff one more time. And there's my issue. Okay, so the equation is pi r squared h. I was using pi d, right? 30 centimeters is the diameter, not the radius. So it should be 0.15 meters. My bad. Let's see if that can give me the right answer. There it is. Okay, so this is not that. It's actually negative 0.00919. Now I do this math and I get, with the negative out front, I get positive 9.19 liter atmospheres. Okay, and now I ask myself, should it be positive or should it be negative? Well, I'm compressing the gas, and when I compress, that should be positive. So there is my work. Sorry about the math issues there. Okay. All right, calculate the PV work done in the following situations. And in this case, let's convert all of ours to joules. Remember, it can be liter atmospheres or joules, but in the change in energy equals Q plus W. Change in energy is in joules, and heat's usually in joules, which means work, if we want to use it with the other things, needs to be in joules. So, a 30 milliliter balloon expands to 200 milliliters against an atmospheric pressure of 1 atmosphere. All right, so work equals negative P delta V. My pressure is 1 atmosphere. My initial volume, or final minus initial, my final volume is 0.2 liters, and my initial is 0.03 liters. Well, that equals negative 0.17 liter atmospheres. And let's get it to joules, though. 0.17 liter atmospheres, and they give us the conversion here. 1 liter atmosphere is 101.3 joules. And so I get a value of negative, so I get a value of negative 17.22 joules. We know it should be negative because my balloon is expanding. Researcher compresses. Compresses means we should expect it to be positive. A gas from 25 to 5 liters by applying pressure of 150 atmospheres. Work equals negative pressure. Change in volume, final, minus initial. Okay, and that gets me a value of 3,000 liter atmospheres, which I can say 1 liter atmosphere, 101.3 joules, which gives me a value of 303,900 joules. Your lungs expand 750 milliliters against an external pressure of 4 atmospheres. You take a breath. All right, so work equals negative P, change in volume. Pressure is 4 atmospheres. And it expands 750 milliliters, so that's just the change in volume. And it's expanding, so that change in volume should be positive. I'm going to change it to liters. Which gives me a value of negative 3 liter atmospheres. I can change that. 1 liter atmosphere, 101.3 joules. And my final answer is negative 303.9 joules. Okay, so just some work doing some change volumes, or some work calculations. And here we have another opportunity. An expanding gas does 150 joules of work on its surroundings at a constant pressure of 1.01 atmospheres. The gas initially is 68 milliliters. What's the final volume? Okay, so we got our work equals negative pressure change in volume. But in this case, they give us the work, 50 joules. They give us the pressure, and they give us the initial volume. We're looking for V final minus 0.068 liters. The problem here is if we were to do this math, the left side of the equation is joules and the right side is liter atmospheres. We can't have that, so we've got to change one of them. It's easiest to change this 150. So let's see, 150 joules, let's change it to liter atmospheres. 1 liter atmosphere, so 101.3 joules. That gives me 1.48 liter atmospheres. Okay, so I can replace this 150 joules with 1.48 liter atmospheres. We still have a problem because it says the expanding gas does the work. If the expanding gas does the work, that work is negative. If the system does the work, it's negative. If the surroundings does the work, it's positive. Here, the system does the work on its surroundings, so it's got to be negative. The system's losing energy. Okay, and now our units make sense, our signs make sense, and we can go ahead and solve. So I divide by the negative 1.01, and I get 1.466 liters equals V final minus 0.068 liters. Add it over, and I get V final equals 1.53 liters. Okay, this is, same equation, but now we have to do a little bit more with the units. Or I guess same amount with the units in a different order. Okay, the figure on the left shows the compression stroke. Right, so this is the it says right there. The figure on the left shows the compression stroke of a diesel engine. How does the upward motion of the piston alter the internal energy of the gas trapped in the cylinder? We know that the energy can be changed by heat and work. When we're compressing the gas, we're not doing any work, we're not doing any heat. All we're doing is work. And again, when you compress, work is positive. So if work is positive, the internal energy must increase. Okay, so we're increasing the energy within our system, which is good because then the figure on the right shows the power stroke as the energy released of a diesel engine as energy released by a rapid combustion of the air and fuel inside the cylinder pushes the cylinder downward. If the gases inside the cylinder are a thermodynamic system, how does the internal energy of the system change as a result of the combustion reaction and downward motion of the piston? Indicate the signs of delta E, Q, and W. All right, delta E, Q, and W. Remember, delta E is just Q plus W. So let's look at heat and work first. First off, we burn our fuel. So the question we're asking is, for Q, is that endothermic or exothermic? Does that absorb heat or release heat? And we know when we burn stuff, that releases heat. So Q must be negative. In terms of work, this is pushing down, so this is expanding. And when a gas expands, it's doing work on its surroundings, which makes it negative, which means my total change in energy must be negative. And that makes sense, right? This is how cars work. When your pistons in your engine get pushed out, or get pushed down in this case, okay, that's taking all the energy in your fuel and it's releasing it through heat and work and pushing your car forward. Okay. State whether Q, how are we looking? 8. State whether Q, W, and delta E for the system are positive or negative. Some water freezes and expands. So Q, W, delta E. Well, it freezes when if you want to melt something, you have to add heat. So if it freezes, it's going to release heat. So Q must be negative. And when something expands, that's all work is negative, which means delta E must be negative. A student heats up an ice cube until it melts. No volume change. What does that no volume change tell you? Well, that means work is 0, right? Because work equals negative P delta V. So if there's no delta V, there's no work. Okay? And you heat it up, so you're adding heat till it melts. So that means my delta E must be positive. Okay, a researcher compresses a gas. If we compress gas, work must be positive, and heats it up, so heat must be positive, so delta E must be positive. This one, QW, delta E. A reaction releases heat, releasing heat, so that's exothermic, so Q is negative, produces several moles of a gaseous product. Remember how moles are related to volume. If moles increase, volume must increase if pressure and temperature don't change. So moles increase, so volume increases, which means work is negative, which means delta E there is negative. Okay, and now we're going to do the similar thing, but we're going to do it with numbers. Indicate whether Q and W are positive or negative and calculate delta E. So we're just going to do the same thing, Q, W, delta E, but we're going to do them with actual numbers here. So some gaseous reactants combine to form a liquid product, releasing 150 kilojoules of heat, so Q is negative 150 kilojoules, and causing the surroundings to perform 75 kilojoules of PV work. So the surroundings are doing the work on the system, and when that happens, that's positive, which means delta E is negative 150 plus 75, which is negative 75 kilojoules. Q plus W. Okay, 44 grams of dry ice absorb 25 kilojoules of heat. All right, so absorb 25 kilojoules of heat. That means heat's going in, so this is positive 25 kilojoules. The resulting CO2 gas does 2.5 kilojoules of PV work on the surroundings. So now the gas is doing the PV work on the surroundings, and that's going to be negative, which means that my change in energy is 22.5 kilojoules. A sample of gas releases 2.9 kilojoules of heat, so heat is negative 2.9 kilojoules. And the surroundings perform 830 joules of PV work. If the surroundings are doing it on the system, it's positive. I'm going to change it to kilojoules so that my units are the same, because then my change in energy is going to be the two of these added together. Which gives me negative 2.07 kilojoules. And the last one here, Q, W, delta E. A reaction releases 150 kilojoules of heat, so negative 150 kilojoules of heat, and releases enough gaseous product to do 275 kilojoules of PV work. So the system does the PV work, so it's negative, which means my total change in energy is going to be negative 425 kilojoules. And that's the end of it. So there you have your introduction and discussion of work and kind of a high-level introduction to heat. Now, the next thing we're going to do in the next problem set, right? We know change in energy is equal to 0 for the universe. Now we're going to break it down. Change in energy is heat and work. We broke down work as negative P delta V, and next we're going to break down heat. It gets a little bit more complicated, but that's what you can expect to see in the next video.